Hey everybody, got the microphone off. Got some 320 questions. Let's do it. Let's hop into some 320. What questions do you have, Kayla? 320. Let me get everything going right here. I think I got assignment 7. Good to go. I've got it loaded up. Hopefully there's no errors. Lots of 201 questions, you bet. 320, then 201. Let's do this. Ella, put all the questions you have in the chat. You don't have to put them all, but put your questions in the chat. And Kayla asks questions away. I've got 320 ready to go. Then we can do some probability or some sampling, but ask your questions, whatever questions you have. Let's do this. Here, I'll hop over to here to the main screen. Let me put in a student. I think good. We're good to go. Let's do this. Describe the relationship. Yeah, let's do it. Can you work through task 4? So task 1, here we're going to put in a student ID, like a fake one. We're going to just go to it and go 55555. So we need to go right here and go, don't put that in, obviously, but that's going to help us generate. Please generate. My sample not found. Did I make it? Please tell me I didn't my run. Everything's right? Everything's right on this, right, Kayla? Where did I? Hopefully, let me check. This should all work. Should all. Oh, good. I don't have string R loaded. I reloaded R. Okay, good. Woo! How to do the market researcher question on the quiz? You bet. We'll do that one next here. We'll do the 320. And then which chapter is that in, Kayla, again? The market researcher, is that chapter 13? Ooh, chapter 13. That's going to be a tough one. Tricky chapter right there. I've done the coding for task 1. Just wondering what do you mean by the question? Describe the relationship between demand and each. Oh, yeah. So I'll show you a cool code for this. So this one right here is task 1, kind of investigating kind of like linear, like you are thinking, like we're not going to so much describe the slope, but we're going to look at the linear relationship between variables. So here we are. There's just always fuzz everywhere. And so I see it out of the corner of my eye and it drives me nuts. There we go. Yeah, it's the pairs command, isn't it? The pairs command is really great because that's why I say to use up here, right? And I'll show you a trick. So, and this actually helps. So the pairs command, if we go to pairs, and we put in the y variable demand tilde dot comma data equals my sample, it will do all the correlations, but I'm going to show you something even better. It makes a correlation matrix scatter plot. There it is. Ooh. Oh. Please tell me I didn't choose the wrong data set. Let me look at my sample. Oh, my. Oh, I need to put this to EX4 bike. Well, this could still be analyzed, right? Yeah, I'm fine with that. Sometimes we get a big analysis right here. So it's treating these. It does have the categorical variables. And what it'll do with those, it'll create like a 2-level thing. So you can see the categorical variables here. And it's creating like a high-low level on those. It's turning them into numeric by just turning it into 2 levels. Do columns exactly, which we do mention in the notes. And so I would do that. There's day of the week. I wouldn't include those. 2 seconds. Sorry, I just sneezed there. And so I would. EX4 bike has less of these variables. So Kayla makes a good point here. Demand is the first column, so we need to concatenate and choose the following. That should do it. Invalid graphic. There we go. That's just the regular error. There we go right here. So I would only choose the quantitative variables. That's kind of key. But the EX4 bike. But do you see this code right here, Kayla? And always we drop hints during office hours when we talk about the assignment. But this is a little bit better and easier to look at. But I'm also going to show you a really cool code, which I think we used once in this semester already. And let me go grab that real quick. Here it is. I think this is the one. Ooh, that's nice. Oh, here it is right here. Okay. So it's under Performance Analytics, Library Performance Analytics. So you need to make sure you have this library. Please make sure to install library. If you don't have it, use install.packages on it. But if you have it, you can just run library. So under Performance Analytics, we need to take core chart. And we're going to take the same my data. So we could take my data here and drop that in there, and that should do it. There we go. Yeah, this really shows it. This is going to, I do not like where it puts demand though, and it does it this way. But so Kayla, this might help out. Let me vanish here for a second. Kayla, looking at this graphic, and we could look at the full data set. Thoughts on the linearity between some of the Y's and some of the X's. So you're only, I wish it put across here because this is the Y-axis we care about. This is the relationship between demand and, there we go, average temp. It is a little hard to read that right there. Yeah, I don't like that the text, nothing's perfect, no graphic's perfect. Average wind speed and demand is this one, but average wind speed and demand is this one. There should be some clear issues to look at right here with this. Like when you think about the relationship, and this one does the univariate analysis of the variable, and that does the bivariate, also gives you the correlation and the statistical significance of the correlation. This is a very good stat graphic. So thoughts on this graphic here, Kayla, and this is what we're meant to analyze. I don't like how it has the demand as the X variable. Our other graphic is going to put demand on the Y-axis if you go across here. So this column right here, this column is the same as this column right here, but I'd prefer to look at this right here because demand is on the Y-axis. Does this all make sense, Kayla, that when you look at these scatter plots, if you're predicting demand, you would want demand right here. Let's see what happens if we don't select. Let's just choose all the variables. It's going to make a pretty crazy graphic. Oh, look at that, non-numeric. It gets mad. It's saying you've got non-numeric argument in pairs, so it is getting mad about the non-numeric. I did see, not with the demand variable, I don't think the notes did it that way. Yeah, so it is a little more complex, and really good point right here. You make sure to have demand in there because investigate the linearity or non-linearity relationship between demand and the 4 quantitative X's in the data frame. Yep, 1, 2, 3, 4. So yeah, I have made it pretty clear that you're only using the quantitative X's. So I think we can take off some points if people don't do it. Also, it's in the video right now. So is this pretty clear right here that you need to make either one of these graphics right here only between the 4 quantitative X's? And we've basically done it. So, and then we need to look at the linearity between it. So you want to make sure you have the Y variable right here and then the 4 quantitative X's. This right here is the best way to look at it because demand is on the Y-axis at all times right here. There we go. Finished up the module notes last night. Yay! So in this instance right here with this graphic, Y and then X is the X. Does this all make sense right here, Kayla, that demand is going to be across all of these on the Y-axis? And then this plot right here that I'm highlighting is the relationship between demand and average temperature. This one is effective average temperature and demand, which is virtually identical. This one is average humidity and demand. And this one is average wind speed and demand. And when you look at these, we can basically do what the advanced command was doing and go right here and kind of draw in what we think the relationship might be. So there's a little bit of something there. Some of them are weaker if you look at them. Hey, Brian, have you done the homework? Yeah, we've done some of them. We're going to do here more in a moment. We're going to do more 320. Upper triangle, then lower triangle is inversed. Yeah, exactly. And you can see it more when you go to this. See, there's a little bit of nonlinearity there. This is this plot right here. Like this plot I'm circling right here is this same one here. It's a lot weaker. It's actually not statistically significant. It's a little bit negative. But you're only concerning yourself with, if you do this plot right here, just look at this where this is the top row. This one is the same information as this right here. It's just they flipped the axes. So, oh, can I actually draw on the pen screen? Whoa, trying new things. So we'll take another screenshot of this right here. And if you were to analyze this data, you would analyze this right here to look at it. But that's the same information as this right here. I just don't like that it puts this demand as the X variable. So it's still showing you the relationship. But this is where you want to zero in on because demand is a variable we always want in there. And if you do it across this way, it'd be the Y variable. But down here, demand is going to be the X variable, which is just a flip of the axes, and you're still looking at a demand versus another variable plot. It's not the end of the world that the axes are flipped. Does that make more clarity right here? We're really trying to investigate to make it super clear what we're talking about here. our main point of concern right now with making this plot is to look at this. And I'm highlighting the form of the relationship to see if we should do linear techniques. If you want this output, let me drop it in the chat. If you want this output here. So to get this output, make sure to install the package that it comes from. And it'd be a little hard to get this wrong now. So there's the code. So it's chart.core from the performance analytics package. So does that all make, so you can put this in there if you want. And can we do the bank loan problem? You bet. We'll do that one next, Della. And then we can do, you got it. And I think Kayla had one more. We'll do that. So does that help out, Kayla, understanding we're really just looking at this right here to analyze the XY relationship and see for any linearity between the quantitative X variables. So hopefully people know to use the quantitative variables. I do like that we use this data set now. So we describe the slope. So we won't really talk about, you'll just talk about like, do you think the linear form is a good form? Let me make sure, let me read my own question. So after to investigate the correlation matrix, make a simple linear model of one of the X variables with demand, run a check regression to see if the linearity condition passes. So when you choose like demand tilde average temp, so let's go here and go LM demand tilde AVG temp, and then data equals. So you need to talk about, to be specific, you need to talk about, investigate the relationship right here and talk about, do you think there's linearity? Like here, I'll just talk about this one briefly. It seems at the upper levels of demand, the relationship starts to go nonlinear. Like that bend right there is of concern to me. So I'm actually going to investigate that right now to see if there is a problem with the linearity. And what do we see when we look at the linearity of it? It doesn't look so bad, but we don't even fail it. So not that question, this one, which one is it? So then we describe the slope because it is used to describe the linear relationship between two variables. For which question is this, Kayla? Number 2, describe the relationship between demand and each of the X variables. Yeah. I would use this graphic right here. So this one has like a positive, mostly linear trend. So I would call this positive, mostly linear. And I don't want to describe them all, but I think you can see it. This one right here, it helps when we see the core matrix because you can actually see the value of correlation. So these can really help. Like you can talk about which ones are strong. So, because, you know, if you pair it with this graphic, you're like, oh, that's the value of correlation. And so talking about the direction of the slope, the strength of the relationship, things like that. Does that make sense there, Kayla? To talk about the relationships between each of them. So describe the relationship between demand and each of the X variables, like positive, negative, strong, weak. It basically goes back to correlation with, I mean, direction of slope is important because that'll be direction of correlation. But coupling these graphics to talk about like just the, great question right there. So yeah, just talking about this right here, like, and these will be big hints right there because you can actually see this one's super weak, not significant, slightly negative correlation, but it's not significant. It could just be 0. And if you look at the graphic, it's like, yeah, it's kind of crazy. This one might be due to some outliers. So yeah, I think you had one more on another problem. So before we head over to 201, can we walk through task 4? That's task 4 at the end, right? Task 4 at the end, right? Task 4 down here at the end. Okay, compare the 3 multiple models. So what you could do, didn't you, what code were you using, Kayla, for smart tables or something? Because I hadn't used that code and I really liked it. Like I saw what you're doing and I want to try to use it here. Was it S table or something? It was some sort of smart table thing or something. And did we, yeah, we'll do your second question here. Best model selected with valid reasoning. VIF shown to be, yeah. So I can talk briefly on this because we haven't created all the models right here, but K cable. Oh, it's in NIDAR, so I should have it loaded up, right? So I should have, what? Library NIDAR. I do have library NIDAR on here. It's so weird. There we go. Yeah, it's in NIDAR. So this is a very simple table generator. It's a simple design. It's not intended to be replaced to replace any other artifacts for making tables. Let me look in here. Let me go to let me look at something. ggplotly table. Tables in R Plotly. Okay, let me look here. That's not a pretty table. I've used this thing before. Well, I'm going to look at this real quick and then we'll... Ooh. I'm not seeing anything that strikes my fancy. Oh, really? That's way prettier. Okay, I have to show you this real quick. Okay. Nah, it's... Here, I'll show it over here. They're showing... That's just cool right there. And so, yeah, you can hover over it. So that's a ggplotly correlation matrix. And I was like, oh, we should make that. That looks way prettier. I'm not seeing a really good table. Okay, let's use this. Okay, K-table. Do you have code with K-table? K-able. Do you have a code with it right now, Kayla? I'm trying to see how to use it. So we can just make a table. We can make... Usually what I do is I make a data frame. So let's say we make a vector here of RMSEs. And we go to RMSE. I'll explain why we're doing this. So we'll just go to RMSEs. And there we go. And then we'll have a vector of R squared adjusted. And I'm just making these up. That would have to be something like that. And everyone's going to do this now. I'm okay with that. I'm okay with this. I'm just doing it the quickest way I'm going to do it. RMSE. And then I'll explain what I'm doing right here. Okay, there we go. So, and we could do this row dot names df concatenate model 1. No. So there we go. So I used it with ANOVA. Yeah, send me your code on that again because I haven't used it so much. And this is the way I would just do it by default right here. And so which of these models would you end up using right now with this information provided to you, Kayla? If this is what you had, which model do you think you would choose from? Model 1, Model 2, Model 3? Which model would you be selecting? And this is a decent way of presenting it. And I think, to me, this looks pretty clear which model would be the best model to use. Like, there's maybe, I don't want to make it obvious like there's a choice. Well, then if I say that, then it narrows it down to 2, obviously. But, oh, wait, careful. So model 1 is a model that's really good with the conditions, but the R squared adjusted is super bad. Like, I mean, it depends. Like, I don't know, maybe the safest statistician in the world would use this right here. But we're usually going to do bad on conditions. Like, conditions are pretty bad a lot of times. Like, but the R squared adjusted on this model is way better. So the best, like, if you rank them, I would probably go with model 2 here. Do not worry. This is like, the problem is like, how horrible is horrible? Like, what are you defining as horrible? Like, how many conditions did we fail? So we could go into more detail. So we might use model 2 because they're virtually identical on RMSEs. They're virtually identical on R squared adjusted. So the best RMSE is going to be this model. This model is the best on RMSE and R squared adjusted because both of these, RMSE needs to be lower, R squared adjusted needs to be higher. And so it does the best on both of those, but its conditions are horrible. So then we get better conditions here, but they're not great. Better conditions here, RMSE is a little bit worse. R squared adjusted is just a tiny bit worse. And this model does insanely bad on both of these. It has a huge typical miss. And when we adjust for how many variables are in the model does way worse. But the model passes conditions apparently, or it does pretty good. So I'd probably go with model 2. And that's kind of my reasoning I would take. Does that make sense, Kayla? On like, this is the kind of thing I want people to think through is like, you know, how do you look at all these things together? And it's just a bummer. So I was hoping for some drawing on. Essentially, we need to find the RMSE and the R squared. Yeah, exactly. This is because it's a lot to like sift through. Like, you know, so you're like, especially if you put it into a bunch of information, Yeah, you're getting it exactly. Like, how would you present this to someone? And I'd probably even highlight this in my report. I'd be like, this is the model I chose right here. Model 2 is selected because, it doesn't do the best on conditions, but we have a good model that has a smaller typical miss and has a good R squared adjusted, which is adjusted for how many variables are in the model. And so I'm going to go with it because no model's perfect and this model's okay. X variable interpreted from the multiple model. I think, tell me if you need any help with any of this. VIFs created. VIF is just going to be, our model won't have any VIFs right now, so let's give it VIFs. Let me go back and get the model and make it get VIFs. So let's give our model VIFs. I have to sneeze so much today. Okay, the model has VIFs now. VIF is variance inflation factor. We will cover this next class. This one has a little bit. It has the, what is the C? It's because there's a categorical variable. But these are basically VIFs right now, and there's pretty big issues right here. Like there's the VIFs right here. And I think it has to do with like a Gini VIF, but these are ridiculous. Your model won't look like this. I can give you what our model will look like. 2 seconds. Our model will look more like, or at least one of your models could look like this. There we go. Now we will see normal VIFs. There we go. Yeah, and they're still ridiculous. So variance inflation factor. So variance is standard deviation squared. So when you think about variance, think about this is a measure about how much more your uncertainty could be. Let's break down what variance inflation factor is real quick. This will be the last class for this week when we do variance inflation factor, or the second class for people. Variance inflation factor. So it's an estimate. And if we think of variance as standard deviation, what's the difference between the two columns? I see the one is raised. Why? Oh, you might have been looking at the categorical ones. Those I don't do as much. I need to go look it up. It's still like the idea between categorical, and I'll take a look here in a second, because really this should be the standard error squared inflation factor. So what will variance inflation factor increase? It'll increase our what? What will variance inflation factor increase? What will variance inflation factor increase? It'll increase our what? And this is a bad thing. You don't want this. 2 columns, GVIF and GVIF, 1 divided by... Yeah, that one, I need to look over that because I don't look at it as much with categorical variables. And the standard error is the what? The standard error is our measure, or basically the amount of what we have in the estimate that we're creating. So I think we use it to create confidence intervals. The standard error is going to be our amount of what. So if we're increasing our standard error, we're increasing our what when we have this. And I can explain how it works. The standard error is our measure of uncertainty. Yep, exactly. It's uncertainty. So this is where you see high variance inflation factor, is when two variables have high correlation. The formula for variance inflation factor is 1 over 1 minus r squared. And that's the r squared sub I, actually, because it's the r squared of the ith variable being explained. So it's actually, how do your x's explain your x's? So you don't want your x's to explain your x's. Does that make sense? I know it's like crazy to say. It's like you make a model. I can show it in the notes, actually. Do we have that? We should have that in notes up, because I don't have those notes up right now. But you make a model using your x variables to explain the ith x variable. Does this make sense, Kayla? So you're going to make a model with your x variable being explained by your x variables. And the larger the r squared, if you think about this mathematically, the larger the r squared of that model, the higher the variance inflation factor, because this is variance inflation factor. So you do not, what is the lowest possible value? So think about this really quickly. Theoretically, what is the lowest possible value of VIF? Like, what's the lowest inflation we could have to the VIF? So what's the lowest inflation factor? And just think about what's the lowest r squared sub I we could get. And that would mean our variables are completely what of each other? Our x variables are completely this of each other. The lowest possible, the I into, yep. So this will be done for each x variable. That's why there's a VIF for every x variable. So the lowest VIF you could have It's a factor of inflation. Exactly, it's 1. Because the lowest r squared sub I you could have, which is the amount of variation in a variable explained by the other variables, is going to be 0. And that's going to be 1 over 1. And that means the VIF is 1. And that means there's no inflation, no extra uncertainty. So when our variables are completely independent of each other, as in they don't have overlapping variation in what they explain, you would have no extra uncertainty. But the more those variables inflate, I wish I had some sort of graphic right here, like as they start to overlap more in what they do, there's more uncertainty. And what would you actually hit? Interestingly enough, if you had this right here, your VIF starts to approach what? It can't actually reach this, but what does your VIF start to approach as your variables are completely overlapping? And then you would just have complete and utter uncertainty in what to use because your variables are identical. Like it's like having the same variable and you're like, I don't know which one to use. So you'd have what amount of uncertainty? It just kind of makes sense then, at least when you think about theoretically, like your uncertainty would be this. You'd have this amount of uncertainty. So your uncertainty approaches what as your variables start to infinity? Yep. Yeah, the variance inflation factor approaches infinity as your variables start to overlap more and more and more in what they do when they bring the variation to the model. So then your model gets so uncertain that it's like, I don't know which variable to use. And it just basically, sometimes it'll give you NA for estimates because it just can't do it. It's just like, yeah, you can't find out the variance inflation for this because they overlap 100% in the variation that they bring. So you don't want that for your models because you're just filling your model with the same data. It's just taking in data, trying to explain a Y variable, and you're like, here's the same data, and it's like, I don't need that. So I should look up, feel free to look it up too. I'll try to look it up in my spare time. The GVIF right here looks very similar. And then they're doing GVIF 1 over 2 times the degrees of freedom. So maybe they're trying to do some standardizing here because degrees of freedom are going to be based on sample size. And yeah, I need to look up about this. There's the degrees of freedom. Okay. So the degrees of freedom, well, it's for how many estimates there are. So the degrees of freedom, days of the week has 6 because it creates indicator variables. So day of the week is going to create 6 indicator variables because the way it works is you have 7 variables. There's 6 indicators and 1 reference level. Working day has 2 levels. Thus we get one reference level and 1 indicator variable. So I don't work with GVIF that much, but I still know you don't want a big GVIF. So, and then I think they're doing a standardizing right here based on the degrees of freedom because you're probably going to see more variance inflation when there's more levels to it, more overlap. So, and the degrees of freedom here are relative to how many indicator variables these are creating. Just like these right here only put 1 variable into the model. So day of the week, if you look at day of the week, it's going to have an indicator for every day, and this is something we'll learn later, but Friday. So you will not see day Friday in here. Oh, we changed the model. You will not see day Friday in here. So if you look Monday, Tuesday, Wednesday, Thursday, Friday is not here. And the reason because the first alphabetical level becomes the indicator variable. So those are things we will be learning, small things like that, like the first alphabetical level becomes the indicator variable. I'm still a little bit confused. I thought the higher the R squared, the better the model explains variation. If a higher R squared increases the VIF. Oh, so no, so that's not the R squared of the model. That's the R squared of the ith variable in the model. So here we'll talk about that just briefly again, then we'll head over to 201. This is the R squared of the ith variable, which is the X is explaining the X. And I might even pull up the notes here in a second. This is not the R squared for the model. This is an R squared for if we make a model. I'm still going to write this. Let me pull it up because I'll write it out incorrectly. So let me show this. 2 seconds here. Can't find my canvas. Hair, stay out of my face. So I'll show the equation. It's an X being explained by the X's, and you don't want a high R squared sub I. That's a good theoretical question. You do not want a high R squared sub I. Does that make sense, Kayla? I know it gets really confusing here with like, wait a minute, we have R squared, we have R squared sub I, we have R squared adjusted. Then there is, what is it? Press R squared. We don't cover that one in this class, but there's a bunch of different ways people can talk about R squared, and it's all variation explained. So we have different types of ways we explain variation. And stop showing my things. And So let's take a look. Oh, I was reviewing section there. Yeah. No, that's awesome, Kayla. No, that's excellent. And we should have R squared sub I. Here it is. Where's variance inflation? We didn't do a partial F on this. There's the R squared sub I, 1 over 1 minus R squared sub I. And here it is right here. So this is the equation right here where you have an x being explained by your x's. And these are just the weights, like the intercept and the coefficient right here. We don't ever really write this out. That's why I didn't want to write it out incorrectly, because I never write this out. I just know that it's a model explaining your x by each one of your x's, and that's where we get r squared sub I. So you do not want a high r squared sub I, because that would mean there's large what? And this is a really great test question too. If you had high r squared sub I, that would mean there's a high level of multicollinearity. So multicollinearity, which should be in the notes here in a second, multicollinearity is when, there it is, multicollinearity. Multicollinearity is not a good thing. It means that your x's are dependent on your other x's. So we have x's explaining your other x's, and that creates larger standard errors, which are shown in the variance inflation factor. So really good review, and this is kind of what we'll be getting to throughout this week. Does that make sense, Kayla? Does this hopefully help out? Like, you do not want multicollinearity, and multicollinearity will be shown when we have a high r squared sub I, and there's the r squared sub I right here. This is different from r squared. So r squared sub I being high is very bad, because that is how we will calculate the variance inflation factor. And the higher the variance inflation factor, the worse it is. If we have a VIF of 1, they're completely independent of each other, completely uncorrelated. Yep. And then if we have a VIF of 5, that means 80% of the variation in whatever x we're talking about is explained by the other x's. So there's really good notes on this. Really great questions, really great working ahead. Kayla, let's throw out 100 points to everybody. We're going to do the 201 question that Ella pointed out here in a second. But thank you so much, Kayla, for asking these big questions, because there's a lot of similar topics, and then all of a sudden it gets confusing. Like, wait a minute, we've already done r squared. That's r squared, right? And it's like, well, that's r squared sub I. So it's for the ith variable in the model, and we have an r squared sub I for every x in the model. Like, they'll all trade places and do their own r squared sub I to see if they are explained by the other x's. So r squared sub I is the ith x variable in the model being explained by all the other x's, and you do not want a high r squared sub I. It leads to multicollinearity, which means there's overlapping variation in your x's being explained by your x's. Super bad for descriptive models, because it adds more uncertainty through the inflation of the standard errors, and the standard error inflation is shown in the variance inflation factor, which is standard error squared. So all this stuff right here, we just did a whole lecture on variance inflation and understanding what multicollinearity is. Like, that, this hopefully should bring some clarity to the topic. So it's a tricky one. I understand, especially seeing that it's like, Kayla, amazing question right there, being like, but r squared is good. I feel like that's the question I would ask. I'm like, yes, r squared is good, except when it's your x's being explained by your x's, then it's bad. So yeah. And what question did Ella? I'm trying to remember Ella's question. Can we do the bank loans and phone company on quiz 13? You bet. Let's do it. And then someone else had some questions too. Please let me know if you had those questions. Let's see right here. I think 1210 I teach. I'm going to get my second cup of coffee here in a little bit. I'm excited about second cup of coffee. We did nearsightedness yesterday. We haven't done philanthropic organization. We did that one a day or two ago. And here are the bank loan ones. Let's do this right here. It's bank loan time. Let's do this. Let's go to the bank and get a loan. Just the last part of the bank. Yeah, that's the tricky part, right? Okay, so the first part right here is the mean for the distribution of the sample proportion. So if we know that 12% of people will make their, the bank believes that 12% of people who receive loans will not make payments on time. I wish it said the bank knows this. Well, it kind of says from past experience. So if they know this, then that's the mean of the distribution, because if 12% of people will do this, then what do we expect to see? That's what we have right here. This is just P. So the equation, let's write it out, because I really want people to study with this. Actually, we have a lot of it from yesterday, right? And so here's the work we were doing yesterday. Do I have a better one with the work not scribbled in so much? Just heard like a weird noise. If I'm all of a sudden abducted or something crazy happens. If my neighbors are like, what? You're always yelling in the middle of the day. Normally distributed with the mean of P and the standard deviation of P times Q over N square root. And this first part right here is mu P hat equals to P, and standard deviation of P hat, that's SD right there, is equal to P times Q over N square root. And so this is this right here. And this is this right here. So that is the mean and the standard deviation. So we're just going to use these formulas. P is going to be the following. Q is going to be the following. That's just the complement of P. And then the sample size, cannot remember what it was. Sample size, what are you today? Sample size is going to be 300. So please remember that P and Q are complements. So they add up to 1 right here. Those add up to 1. P and Q add up to 1, and we're good to go. So let's take a look. Okay, so let's solve the formulas. And we go right here. And we do P times Q, complements of each other, over N, square root. There we go. Delete the decimals, and we're good to... It's going to round up, isn't it? That's a bummer. Okay, so our 3 conditions. Ella, what are the 3 conditions? Condition 1. So we need to know condition 1 is always this. Condition 1 is always random. This means they need to randomly select the people that they're going to give loans to. Condition 1 is random. Condition 2 is less than 10%. And that one's super confusing because it's like, wait, less than 10%? Has to deal with the mathematics. I go into detail during class on it, but we sample less than 10% of the population. Condition 3 is success failure. We need to have at least 10 expected failures. So at 12%, we would expect at least this many people to not pay their loans. Exactly, random 10% success failure. And we do pause in the middle of it to make sure when we get to that third condition, we say the right third condition. So make sure to pause right there before the third condition. But we did a lot of practice of this yesterday when we did all of the conditions right here. So we should be good on all of these. With reasonable assumptions, they're all met. Just make sure you know those conditions, practice them, random 10%, and then pause. Now here's where it gets tricky. So what is the probability that over 14% of the clients do not make timely payments? MuBot's going to help us out right here with the David M. Lane applet. So MuBot, tell us about that David M. Lane applet, and let's go over to it. We do need the standard deviation, and I think we can use the one we used up here where we round this. So using the rounded version of the standard deviation, thank you, MuBot, you're so helpful. There we go. So here's the David M. Lane applet, and we're going to put in the standard deviation, and then we're going to put in the mean, and then we're going to go above the number it gave us, which was 14%, and then we're going to take the probability right here, and that's got it. So let's talk briefly about what we have. I hate that it's almost exactly 14. Be careful on your rounding. We got it. Should have took a deep breath. I was a little bit scared there. So what we are doing is we are saying what is the probability that 14% of people don't make timely payments? And let's look at the graphic. Looking at the graphic, what percent of people do we not expect to make timely payments on time? Like if we take a sample of 300, what's the most likely proportion of people to see to not make timely payments? If we take a sample of 300 people, what is the most likely proportion of people to not make timely payments? Like just think proportion-wise. Don't think amount. Just think like, if I took a sample of 300 people, it's most likely that this proportion would not make timely payments. If I took a sample of 300 people, what is the most likely proportion to see to not make timely payments? Exactly, because that's the mean of the distribution. You'd be like, probably about 12%. Now, what do you notice about 14%? 14% is almost exactly what? And if we did this, it would be exactly that. 14% is almost exactly what? This would not be a horrible test question. This would not be a horrible test question. And let's figure out the z-score of this, because you can also do this, which you can probably tell what the z-score is going to be very close to. So observation minus mean over standard deviation. There's the z-score. And the z-score is very, 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 very close to what? It's very close to 1. The z-score is very close to 1. And when you think about this, the area above 1 is how much? Like if I use the z-score right here and go back, and do the z-score for it, which you can do, you will get the same answer. So using the z-score, 1.0526. You will get the same. You will have to calculate the z-score by hand. You won't have to calculate the p-value by hand, but a test question could give you the following choices. A test question could give you, it could say, what is the p-value for this? And it could give you the following choices. So here's a theoretical test question asking you what's going to be the p-value. And it could say A, it could say something like 20%, B, no, 18%, C, 14%, and D equals 1%. So this is a possible question right here. And how would you know the answer to this? How, if these were the choices, your drawing is going to help you a bit, but you might be between a few answers. So how would you know the answer to this and be like, okay, it has to be this? How would you know the answer to this? Because we can see the answer if we just scroll down, but how would you be like, I know the answer to this. It has to be this answer. One of them should kind of stand out and you could then eliminate another answer. But you could be between a few answers right now. You could be like, I don't know. That could be like 14, 18, or 20%, right? Like that's not 1%. And you can also show it's not 1%. But looking at this graphic right here, I know which answer it is. Like I would instantaneously know, which we rounded it. It's like 15% actually if you round it. So that is the answer we would pick. And why? Because above 1 is how much? How much area is above 1? Above a z-score of 1 is 16%. So if this is 16%, then how much has to be below 1? Less than 16. Does that make sense? Or how much has to be there now? So there's less than 16%. If you look right here, does that make sense? My data glitch, can you... Wait, I'm so sorry. I don't understand, Kayla. I don't understand, Ella. Oh, what do you mean? Can you reset? Oh, your video glitched or something. So with this right here, this has to be less than 16% because above 1 is 16%. So above 1.05 has to be less than 16%. Does that make sense? So understanding the graphic and the empirical rule that when we go between 1 and -1, we have 68. So above 1 or outside of 1 is going to be 32. And so this is 32. And then above 1, if we go above 1, is going to be, wait, that's below 1. So above 1 is 16, and we're at like 1.0524 or something. So it's going to be closer to that. So when you look at the possible answers I put on the screen, it has to be less than 16. So the only answer that worked for less than 16 was 14%. And you say, well, what about 1%? Well, above 2, if you know between 2 and -2, so if we go between 2 and -2, there'll be 95%. And so if 95% is inside, then 2.5 or 2.5 is on either side. So there's 2.5 on either side, meaning, well, there's the 2.5. So above is 2.5. Now, if you notice, these numbers are not exact. We're not exactly getting, yeah, awesome. I think you get it, Ella. The numbers are 68.26, 95.449, and 99.73. And I always like to show that we can get these more exactly if we do something like R right here, where we go, I think this is it, really quickly on this. Good, and then, so 68.26, p-norm. 68.26 or 27, oh. And then 95.4499, I just learned that yesterday. There's the 99 and 99.7300. It's got 2 zeros after that. There we go. So, oh, and I should remember the 2 zeros and then a 2. There we go. Memorize more digits. That's what I like to do. I'm not joking. I actually like to memorize stuff. So 68.268 bounces back to the 8 right there. Interesting. But we just call this 68, 95, 99.7. So we don't, like, we're rounding it. We're being nice with our rounding because we don't want to say 68.26, 95.4499, 99.73002. It's too much. It's too much. 68, 95, 99.7. And that's why the numbers aren't exact when you do this right here because there's more decimals that we're not carrying out. Let's look at that other question. So we got that one right. Was it the new restaurant one, Ella? What was the other one you want us to do right here? You said the banking question and then phone company question. Phone company. Here we go, phone company. Let's do it. For the Canvas content quiz, there's a casino question. For that, do we just multiply the probabilities of each different probabilities together? Maybe. If you put the part of the question in there, it just depends. It sounds like that. All of them, which this one right here, we can do this one here next. So a market researcher for a phone company surveys 131 people. So let's go here and let's take the data. Let's bring it over. Here we go. Okay, so if they survey 131 people, then that makes that the sample size. So 131, always mark your notation. We should have done this in the last one. Is sample size. And who are likely to switch when their contract expires is 12%. So this is the known proportion. Yeah. They really don't make it sound like a known proportion right there, but that is a known proportion because it says, what is the standard deviation of the sampling distribution of the proportion? So it's asking for the standard deviation, which is equal to, I should put it there. P times Q over N square root. So this is the standard deviation for the sampling distribution of the sample proportion, and we're going to see something interesting with this question. Now we need to know what Q is. Q is just the complement of P, and we have the same one, ironically, as we had last question. So Q and P are complements of each other, which mean they add up to 1. So let's go ahead here and do P times Q over N square root, and then just copy paste into there. So we now have the answer to what is the standard deviation for the sampling distribution of the sample proportion. My copy paste does not work from this calculator. 0. And round to 4 decimals, 0.0284. So this is where it gets interesting. And there's actually a quick way to solve this, a very, very, very quick way to solve this. It says if she wants to reduce the standard deviation by half, how much larger should her sample be? Like, how large should her sample be? This seems like a very complicated question until we look at it. And if Kayla, if you're still here, you're going to love this because this is a much easier problem to solve if we do it mathematically. So if we just do this mathematically, it makes our lives super easy. Let's say we go to the standard deviation right here and we want to get half of it. So let's go right here and just multiply this by a half. Would you agree that this is going to reduce her standard deviation by half? Does that all make sense? Like, Ella, if I do this right here, will that make it so that we have half the standard deviation? Like, I just multiply it by a half. Like, wouldn't that just do it right there? If we just multiply it by a half, we would get half the standard deviation. But we're going to run into a problem. Can you just multiply these things together? Would this just like, would this 2 just go inside of here? Like if I take this, would this 2 just go inside of here right here? Can you just like algebra these things inside of each other? So this, we can fix this really quickly. Can we just algebra this inside of here right like that? And the answer is we can't. What do we have to do to this? We have to go right here and let's do the following. How about we do this? Would you agree with me if I do this right here? If I go like this and then do this, I've just undone that. And you could go right here and do this. Would you agree with me that I have now squared and square root? Like this is the same thing. Does this all make sense right here that that's the same thing? Like this right here is the square root of 1 squared, which is just 1. This is the square root of 2 squared, which is just 2. Does that make perfect sense? Does that perfectly on board with that? Like that's the square root of 2 squared, which is still 2. So we're still just multiplying by a half. I squared it and square rooted it. Perfectly fine. So how about now we just change this? I mean, isn't 2 squared and 1 squared, aren't they just 1/4? Now, can I take this this whole thing right here, if it would let me take it, can I take these two things and multiply them together? Can I multiply these two things together and put the 4 inside of here? And now the answer is, yes, I can. So now they can be multiplied together because they're over the radical and you can multiply things in a radical together. It's a little bit of algebra right there. Makes our lives way easier. So what is the answer to this question? We've just shown mathematically what the answer is. Can you tell me what the answer to this question would be to get half the standard deviation, what you would have to do? To get half the standard deviation, because the answer is right there. So what is Brian going to do, and what would his answer be? I'm trying to think. I'm doing it in my head right now. I'm going to get it wrong. I'm just so tired today. I think I know the answer. I think I've got it solved in my head. Because that is the answer. So what would the answer be? Because that is the answer. What would the answer be? And so this is a little bit tricky of a question because it is a bit of algebra. But we're just going to take 131. There we go. That's got it. Can I not copy from this anymore? I can. There we go. Well, and so well, I can't even speak today. That should be half of it. That should be half the standard deviation. So I think you are correct. So that is half the standard deviation, but the sample size associated with that would be 4 times this. Does that make sense, Ella? So that is half the standard deviation, which also shows mathematically we did find half the standard deviation, but the sample size would be 4 times the original sample size. And so, yeah, no. So yeah, you're on the right track. So great job solving right there. That is half the standard deviation, which confirms we wanted to reduce it by half. So you have confirmed, which is excellent to do, that we did reduce it by half. But then the question is, how large of a sample size would we need? And how large of a sample size is the following. No, Ella, let's throw 100 points. Don't worry, you're here to practice. This is what it's all about. And understanding the standard deviation, the mean of the distribution, also the outcome of the wheel is independent of the two different outcomes. Oh, this one right here, yes. Each wheel has 10 equally likely spaces. Oh yeah, keep posting it. And then what does it say next? So here, let's write out the question. So we've got a wheel, and they're all equally likely. It has 10 spaces. And so let's draw out our wheel. And 10 spaces. I'm going to do a horrible wheel. Okay, those are equally likely spaces. If you play the probability, you get a lemon and a cherry and a bell. So the lemons, the skulls, are going to be skull, 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 skull. And then lemons are 3 lemons. And then cherries and bells. And they're equally likely. There's the skulls. There's the lemons. And here's the cherries. And here's the bells. So the probability we're talking about right here is you spin the wheel. Let's go on, stop our things. So you spin the wheel. You might have it. I think you're right. Yep. So it's the probability you get. Let me look here. A lemon is 30%. Yep. Then you get a cherry, and then you get a bell. That'd be accurate. So that's, let me think here. It's going to be is it 0.006? I think it's 0.006, right? I think 0.006. Maybe. Not to give away an answer, but I think so. 0.006. And great work right there. I am so tired today. One of these days I'm just going to sleep. Sleep for a long time. A confidence interval of a population portion has the limits this. What is the margin of error? So when we do the margin of error, what we need to do is we need to take half the length of the interval. So the margin of error, I want you to think about this. Here's the way to think about margin of error, and this is a good way to memorize it. Your friend says that they will show up at your house sometime between 4 p.m. and 5 p.m. Your friend says they will show up at your house sometime between 4 p.m. and 5 p.m. When do you think your friend will show up? When do you think your friend will show up? Like, when would you guesstimate your friend would show up? So your friend says, oh, I'll be there between 4 and 5. When might be your estimate of when your friend would show up? Like your actual estimate. So this is another type of way we could ask the question. Like, what is the center of the interval? What is the estimate the interval was created from? So your interval right there works the same way, 4:30, exactly. So I like looking at these questions with things we already know, like your friend says, I'll be there between 4 and 5. You're like, okay, well, around 4:30, I expect you. Doesn't mean they will show up then, doesn't mean they'll show up within 4 to 5, it just means this is their estimate. So what is the margin of error of this interval? So what is the margin of error? What is the plus or minus on this interval? And then we'll look at how we did this mathematically. So what is the margin of error of this interval now? What is the margin of error on this interval? Like, what would you say is like 4:30 plus or minus this? So now that we found the center, we can find the margin of error, which is just the plus or minus on the interval. And you can do this mathematically, or you can kind of look at this one now that you have it drawn out and you can be like, just like how much plus or minus is that? Plus or minus 30 minutes. Exactly, that's the margin of error. So when you think about the margin of error, it's what the length of the interval. So you just have to type 4 letters here, but the margin of error is what the length of the interval. So if you look at this right here, the full interval, and the margin of error is always this, the length of the interval. A good way to remember it and think about it visually right here, the margin of error is always what the length of the whole entire interval. If you look at the whole interval, the margin of error is always this, the length of it. Half the length, exactly. So how could you get the length of an interval? Well, we could just take the upper minus the lower. So let's put here upper minus lower, that's the range of the interval, divide by 2 equals margin of error. So the margin of error is going to be half the length of the interval. That's one way of getting it. You can get the center of the interval by taking the upper plus the lower and dividing by 2, which is the average of the interval. So if you take the upper plus the lower and divide by 2, you will get the center of the interval. I guess I could have just turned that into a plus. And this will give you the center. And try not to memorize these. Try to think through them. Yep, you got it, Ella. I wouldn't try to memorize these. I know like you're memorizing them by thinking about them conceptually, but it's better to put into your head conceptually that the margin of error is half the length of the interval. The center of the interval is the average of the two values. And then you're actually memorizing the formula by memorizing the center of the interval is the average of the two values. And the margin of error is half the length of the interval. So hopefully, I just think it makes more sense to kind of think about them theoretically here and rather than memorizing them. And yeah, so 2.8 is the margin of error and 67. Yep. I don't know if it asks the center of the interval, but that does look to be accurate. Your mathematics, if your mathematics are correct, then everything's good. Excellent job. Hopefully this is making sense here, Ella. Great job. You're working really far ahead. Really, really excellent job right here. Great, great work. I hate that it keeps moving the cursor. I think it moves the cursor back to where I was at. I think that's got it. We'll head to space here. Click the wrong button. But great work today. We got through a lot of 320. We did some 201. We did some advanced 201. Ella, you're getting ready for the test right here with all the material. Like, you've basically done the material up to the test. No, you're doing great. You're way ahead. You're doing excellent work. Put on a little music here and end in a moment. We'll put on this one instead. No, I think you're way ahead of the game right now. You're asking the questions about material that we need to learn, and I think you're on track. Like, I'm proud. Like, I think people are going to do well on this test. You just have to be practicing it, because is it starting to make more sense? I hope. Like, just that whole interval thing. No, all the p-values make sense to me. Is that, wait, they make sense or they don't? I'm hoping they're starting to make sense. We have time. We have over a week right now. We have a little bit more than a week. And with a little bit more than a week, we can practice. And we can figure out what we don't know. And then we can get ready. And then we can get an A on the test. If it's the night before the test, then we're like, okay, now we have to cram. And that's when you're just like, okay, gotta learn. But right now we can practice. We can figure out what we don't know. And that's what we should be doing. Head off here in a second. Oh, I just feel so tired today. I don't know. Anyone else feel that Tuesday? I'll just like go lay down. Everyone's like, what happened to Brian? He went to sleep. It's show week for my dance company. So, oh, I'm so sorry. I can understand. I actually had one of my students who was on the UT dance team that won like the nationals. Do you remember, this would be like 2015 or 2016? I don't know how big UT dance company is nowadays, but she was on the dance team at UT that won nationals. And she came into class wearing a gold medal around her neck. And I see it and I was like, is that a real gold medal? And she was like, yeah, it is. And I was like, oh, okay, cool. And she's like, yeah, we won nationals. And I was like, oh, that's awesome. But so it's really cool. Like, I wish I had skills like that. I watch a lot of K-pop and they dance a lot. And I'm like, man, I wish I could dance. Can't dance. It's one of those people. I play piano and then people think I can sing. They'll see me play piano and they'll be like, you can sing, right? I'm like, no, I can't sing. They're like, but you play piano. I'm like, it's totally different things, singing and playing piano. They're like, but you have a deep voice. I'm like, doesn't mean I can sing. I just play piano. That's all I do. I don't know. Well, with that, we'll put on our last song of the day. But no, good luck with that Ella right there. As you know, practice makes perfect. Practice makes perfect. We have to practice statistics. We have to practice piano, whatever we're doing in life. The more we practice it, the better we get. So let's practice up statistics. We got this, everybody. You're welcome, Ella. Great job and good luck with everything. You got this with your show week. Good luck, everybody. I will be back. I already clicked the button. Bye for now, everyone. Bye.